Yes, thank you. Yeah, so I'm Damien Vreug, and in the next 20 minutes I will talk about iCoLa, which is a compositional meta-language, and the main focus of this meta-language is on exploring the design space of languages. So we see a lot of new programming languages being created, and that makes sense from the kind of point of abstraction, because high-level programming languages provide a great abstraction mechanism. We can either, for example, increase safety while retaining performance in the case of Rust. We can encapsulate domain knowledge to make it easier for domain experts to either use our language or communicate with language engineers. An example of that is P4 for network engineers. We can also increase productivity and maintainability by having better ways to express ourselves, etc. There are many properties that give languages a nice form of abstraction. And language-oriented programming is a programming style that basically takes this and makes it the main point of development. So when you have a problem, you especially design a language for that problem, and from there on out you solve your actual problem. However, creating a programming language is not trivial, as most of you probably know. To make it actually usable and polished, we need a large engineering effort. So we first need to make it runnable, either in the form of an interpreter and compiler. We need a parser for that. We need debugging support, good documentation that is up to date with our current language. And we might need either editor services in the form of language server protocol, or we need an IDE integration. Luckily, many people have done work on this, and language workbenches can help us here. They often have some kind of way to describe a language, for example, the concrete syntax and a possible semantics. And from that, with a bit of help, you can generate most of this tooling automatically. However, creating programming languages is not just an engineering effort. It's also a design effort. So you might have a design in our mind, we create an implementation of that, we test that implementation out, and based on the testing, we feed back into our design and make changes. And here, the user in the loop can be different. In the early stages, it might just a language designer that tests their own system and then integrates it in the design. But at later points, that are actual users that have feedback on your language. And if we look at most general purpose programming languages, we see this happen a lot, where the first design is often not the most optimal design. And eventually the programming language evolves and we get to a new design, which might break backward compatibility, which requires a large engineering effort to transition to the new design. So what iCoLa aims to do is to accelerate and manage this feedback loop to help identify erroneous design decisions early on by retaining the benefits we get from language workbenches. It won't be possible to remove all erroneous design decisions, but hopefully make it a bit easier to catch these decisions early on and help the design effort when designing a programming language. And this is a high-level overview of the iCoLa language, the iCoLa system. So it's basically divided in two parts. We have a meta-language, which consists out of operators, which essentially define language constructs and semantics. And then we have language definitions, which utilize operators to define languages. And language definitions, they give the language structure. They can specialize operators to their semantics, and they can do adaptability to adapt languages to the environment in which they are run. Then these operators and these language definitions, they function as input into a meta-REPL. So language designers can define their language inside this meta-REPL. And from this meta-REPL, they can instantiate a REPL for the defined object language. They can then test it out and then go back into the meta-REPL, make different choices regarding the design, go back into the language REPL, etc., etc. And at the end of this process, we get a number of languages out that we can share with the community and get feedback on. So let's take a bit more in depth on these specific components. So the operators in our language are based on initial algebra semantics and are split into two parts. We have operator definitions and operator semantics. The operator definitions they introduce a name. So every operator has a unique name. It has an arity and it has operand positions. Then the idea is that operators are defined independently and can then be composed together and are meant to be immutable. So we define an operator and its semantics once, and then we can reuse it across many languages, and then we don't have to redefine or change the semantics of the operator. And then we have operator semantics, which are essentially functions from the operator to a semantic domain. And then our approach is not bound by a specific semantic domain. As long as we can write a function into the semantic domain, it can be integrated into our system. And here is an example of two operator definitions. So a simple add operator, which has two operand positions. In this case, we name them add left and add right. And then we see a semantic function that translates this operator into the semantic domain of functions, which is a component-based semantic approach based on implicit modular structural operational semantics. And this is a rather expressive semantic domain as it supports a wide variety of programming paradigms. So by selecting this as our semantic domain, we inherit that in our approach. And an important point with semantic functions is that it's based on initial algebra semantics, so the subparts of the operators are already translated. So in case of add, here the left and right component, they're already translated into the semantic domain when we translate add into the semantic domain. We also have an example of print here, which has a simple expression, and then it prints the value of the evaluation of this expression and a new line. And it's important to note there that we haven't made any decisions regarding the structure of the language. So as of yet, we can't actually use this because it doesn't say where, for example, we can use add operators or where we can use print operators, etc. No, that is done by a language definition. So these operator definitions are used by language definitions. And a language, we define it as a structure defined in terms of this set of operators. And this structure can be split out into three components: language structure, specialization, and initialization. And language structure can again be split into two parts: sort constraints and the top level. And with this idea of a language, we can support language composition. So we can take two languages, compose them together. We also have the notion of an empty language, and together that makes language as a monoid. And because of this, we get incremental programming for free and support agile language definitions because we can quickly change the language structure in our meta REPL. So what do I mean with language structure? Our language structure is defined in either sort constraints or the top level. And sort constraints are also defined in two levels: operator assignments and subsort declarations. And sort constraints essentially determine which operators can occur at which operator positions. So here I have an example where we again reuse our add operator. This has two operand positions, add left and add right. And in this example, we assign a num operator to the left side and a num operator to the right side, and also an add operator to the right side. So in this encoding, we encode right associativity into our language. Now, if we have many operators, this can become kind of tedious. So what we can do is we can introduce an auxiliary sort to reduce repetition. So in this case, we introduce the expression auxiliary sort, assign the number operator and the add operator to this sort, and then we can use a subsort declaration to distribute our auxiliary sort over a certain operand position. So in this case, we distribute expression over add right. And now if we want to extend our language, we can just grab a new operator and assign it to any of our operand positions. For example, to the expression subsort, then it automatically gets included in the add right, but we can also decide I only want it on the left side of addition. This way we can create a variety of different languages quickly. Then we have the top level, which essentially determines the entry points of the language. So let's say you're in a REPL, then this top level determines what you can enter as the first construct in the REPL. Then specialization. So the right operator semantic depends on the language. And we want to reuse operator definitions as much as possible and have them kind of immutable. So let's say we have a simple if operator. This has a condition and then a body that is executed when the condition is true and a body that is executed when the condition is false. Now, we translate this into the semantic domain by just using the if true else function, which does what you expect it to do. However, in this semantic domain, the condition must be a Boolean. And that does not work for C-like languages, because there the condition can be an integer. And based on the value of the integer, it determines which body to execute. So what we can do is we can introduce a new operator, the if C operator, which essentially is the same, except for a small change. So instead of just having our condition, we now have a not is equal to 0, which wraps our condition. And we now see a lot of most of our if operator is now duplicated in our if C operator. So what we want to do is reuse as much as possible, and we achieve that by associating glue code with sort constraints. So here we have a sort constraints which assigns C expressions. So we have a sort of C expressions which contains a bunch of operators, and we assign that to the if condition. And with that assignment, we also associate glue code. So what happens now is that when an operator is part of the if condition and also part of the C expression, And when we translate it, it's wrapped in this semantic function. So when we translate this C expression to the semantic domain, this result is now wrapped with the not is equal. And this only happens for the operators that are part of the C expression group. So let's say we have a C-like language, and now we want to extend it with actual Booleans. We can just introduce the Boolean operator, assign it to if condition, but not to C expression, and that works fine, because this glue code is only done conditionally on the C expression. And this way, we remove the duplication of having the need to introduce multiple operators. We can instead use our original if operator. Then we have initialization. Initialization is actually just glue code over the top level. So it enables you to modify the top level behavior to adapt the language to different environments. So let's say we are running in a REPL environment. There we might want to print uncaught exceptions and not stop the REPL. And we might want to print the evaluation of expressions. But when we are running in a production environment, this is not exactly what we want. So via initialization, we can adapt the semantics of our language to these different environments. Then we have our this meta language input into our meta environment, which is, as I stated, divided into two parts, and these can be switched pretty easily. So here I have an example session in the iCoLa shell, which is how our meta environment is called. And this always starts with the empty language. So by default, when we start the iCoLa shell, we just have the empty language. What we then do is we compose it in this example with the add language. So for that, I use the Haskell semi-group operator, which in this context is language composition. And our current defined language is the empty language, and we compose that with the add language. So then as a result, we get the add language. We then commit this. So we choose this language, and then we are put into an object REPL for this language. We can then try it out. So what we do from the specification, we can generate parsers, and we do that in the style of a Lisp-like parsing syntax to prevent introducing ambiguities. So by having this, we can still experiment with the object language without having ambiguous parsers. So in this example, we now do a simple expression. We add 2 and 3 together, but we don't see anything because our language only contains add constructs and a number construct and nothing else. So we exit out of the object REPL. We are placed back into the meta REPL, and we extend our current language with the print language. So what this does, this integrates the print operator into our language. We go back into our meta REPL, and we can now add the print operator and use it, and we now see our result 5 as the addition of 2 and 3. Now, that's great, but maybe the print operator is a bit too much for the language we have in mind. So we go back into the meta REPL, and we use exploratory programming to go back to a previous state. So in the meta REPL, you see different numbers. They essentially encode the current context we are in. And by doing the jump command, we can go back to a previous context. So in this case, we jump back to the context 3, where we did the composition with the print language. So that still has to happen. So instead of composing with the print language, we compose with an anonymous language in which we integrate initialization code. And in this case, we do printing. So what we now do is we print top-level evaluations. Then we can go back into our object language, and now we can use the operators as we had in mind, where we can add 2 numbers together and get 5 without having to use the print construct in our approach. So we implemented this as an EDSL inside Haskell, where we leverage template Haskell and data types a la carte. And the nice thing about this is that the sort constraints, so essentially where you can use operators, are enforced by the template Haskell or by Haskell type system. So for example, if you would write a parser for one of these defined languages, you would not be able to construct a language that does not abide by the sort constraints that you specified. Furthermore, we also have the full power of Haskell available. So on the right side, you see an example of our EDSL, and operators are defined as GADTs. So here we have an example of the add operator. Then translations into a semantic domain are implemented as type classes. So we can give an instance of this type class for our operator, and that translates a certain operator into a certain semantic domain. And then languages are just data types defined in terms of template Haskell constructs. So in this case, we have an add language. And what we see here is that we can just use regular Haskell. So we just have list comprehension available in our EDSL. And With this, languages are first class inside template Haskell. And what that means is that we can just write functions over languages. Just regular Haskell functions in terms of template Haskell constructs, we can just write those. So let's say I want to refine a language. So I want to remove certain constructs of it. We can just implement that as a function. So here we have an Haskell function that takes in a language. And what it does, it removes the less than equal operator out of the operator assignments and out of the sort constraints. And it doesn't matter which language this is. It's just parametric. So we can input any language. And we can also remove other operators if we wanted to. We just have the full flexibility of Haskell available to refine languages to our needs. And being first class, we can also, for example, implement functions that do automatic generation of parsers, which is what we do with the Lisp-like syntax. But it's also possible to implement parametric languages. So, for example, you have languages that get, for example, a Boolean to denote that we're running in a REPL. And based on that, you get a different configuration. And we are currently looking to use these functions to generate language tooling. For example, implementation of the LSP or debugging support. We want to define that also as regular Haskell functions. So iCoLa is still ongoing work. So currently we have an implementation as an EDSL inside Haskell. And this is generally nice in our implementation because we were pretty quick to prototype new ideas and try different things out. But language definitions can be rather verbose. And it doesn't directly map to the conceptual model we had in mind. So one of our ideas is to make a hybrid DSL in which we can define our external DSL, can define our languages in an external DSL, but then still make this available to engineers inside Haskell, so that users still can write regular Haskell functions over language definitions. We're also exploring the integration of user-defined concrete syntax. So currently we generate these Lisp-like syntaxes, which is not amazing, but it allows you to prototype with it. But to integrate user-defined syntax, we of course get ambiguity, and we're currently looking at ways to solve that. For example, using GLL parsing or any of the parsing mechanisms. Also interesting is the exploration of alternative semantic domains. So our system is not bound by a specific semantic domain. If you can write a type class instance in Haskell to a specific semantic domain, our system can integrate it. Currently we use funcons, but it might be interesting to explore other semantic domains. So we're looking at that. And lastly, we are looking at language synthesis. So on the right, you see an example. So what we did is we defined our model in terms of graph rewriting. And that way we can essentially check all possible languages that are possible with a set of operators. And then using that, we want to figure out if there are certain language configurations that are suitable to automatically generate. So let's say you're in a design process, and while trying out things, you get a possible recommendation. Hey, maybe this configuration is useful for you, and you can try it out. And that we want to do in the context of graph rewriting. So iCoLa accelerates the feedback loop via incremental language development with reusable components. And if we look, we can see where this kind of happens. So with reusable operators, we aim to go quicker from design to implementation. And then with incremental language definitions, using this implementation, we can create many language variants and then give this to users. Then we get user feedback, and that we can integrate in the iCoLa shell to try out how this affects our system. That then functions back into the design, and then we go to a new implementation, etc. Of course, these aspects are not only on these edges, they're also on other edges, but this is where they mainly contribute to our system. Thank you for your attention.
Questions?
So at the beginning, you said you want to help developers to avoid kind of erroneous design as early as possible. Can you give us some concrete example of such an erroneous design with you can avoid by using iCoLa?
That's a good question. So in our case, some examples that we are trying to figure out is one system. My supervisor is working on a norms on a DSL for norm specifications called eFlint. Essentially, the goal of that is to try to encode law inside executable system. And there we are currently in version 4. And we saw several design decisions that would have been caught, I think, pretty easily with iCoLa by just trying out how different aspects in a language can be used. So for example, adding different operators and then seeing how they affect the system, that would be pretty easy in iCoLa.
So you say you can easily put a new operator or
Yes.
remove it.
Yeah.
So that's kind of trial and error basis.
Yeah.
Thing is
Yeah.
supported. Okay.
Exactly. Yeah. And then you can share it with the community and get feedback on it. Yeah.
Yeah, interesting work. My question is about effect interaction. So you said that you can basically compose different languages, and these languages may have different side effects.
Yes.
You sort of get them off the shelf. But for different effects, they may interact differently, right? Could you also get this effect interaction in your system, and how?
Essentially, yes, but it kind of happens at the glue code. So I haven't shown it here, but so the glue code here is essentially applied conditionally, but it might be that multiple languages define glue code on the same operator. And then it's determined by the way we compose these together, how those effects are integrated. So by switching the composition, you might have different effects.
Okay, so you would have to rewrite all of these. Okay, well, I'm curious how you would deal with, for example, transactional exception catching, but maybe we can discuss that offline.
We can discuss it, yeah.
I also had a different question, basically about, well, this slide here. You have different sorts here. What is the point of having different sorts for if cont, if true, if false? Is that to deal with glue code, or is that for some other reason?
So that is to split operator definitions from language definitions. So we essentially do not make a decision here. When we define an operator, we do not make a decision which operators can occur at which place. And let's say we would have the same sort here for all the 3 locations. And if we assign one operator to one sort, it automatically occurs at all the 3 locations. And that might not be something that we want. So in this case, we take it very finely, where we say every sort is different. But you might, for example, say that the bodies, they have the same sort. That would be possible.
Okay, thanks.
Thank you.
Okay, thank you again.